Demystifying AI, a beginner's guide to building your first neural network with Keras. Coding AI with modern libraries is easier than you may think. It may sound foreign and complicated at first, but starting with a simple example, you'll see how easy it can be. In this tutorial, we'll walk through the steps to build a simple AI model in Python using the Keras library. This is what we'll do in this tutorial. Import necessary libraries. We'll start by importing essential libraries such as NumPy, Pandas, and tools from Sklearn and TensorFlow Keras. Load the dataset. We'll use the iris dataset, a classic dataset in machine learning, to train our model. One-hot encode the labels. We'll encode the target labels using one-hot encoding to prepare them for the neural network. Split the data into training and test sets. We'll split the dataset into training and testing sets to evaluate our model's performance. Build the model. We'll create a sequential neural network with 2 hidden layers and an output layer. Compile the model. We'll configure the model with an optimizer, loss function, and evaluation metric. Train the model. We'll train the neural network on the training data for a specified number of epochs. Evaluate the model. We'll assess the model's performance on the test data to see how well it generalizes. Make predictions. We'll use the trained model to make predictions on the test data. One-hot encoding is a way to turn categories into numbers that a machine learning model can understand. Instead of using a single number for each category, we use a list of zeros and ones. For example, if we have 3 categories like red, green, and blue, we represent them as 100 for red, 010 for green, and 001 for blue. This helps the model know that each category is different without assuming any order. Before we dive into the code, it's important to approach AI development with an open mind. While it may seem complex and daunting at first, modern libraries like Keras make it incredibly accessible, even for beginners. You don't need a PhD in computer science to start building AI models. With just a few lines of code and some basic understanding, you can create powerful AI applications. So take a deep breath, follow along step by step, and you'll soon see that developing AI is well within your reach. Let's get started. Step 1. Import necessary libraries. The first step in our AI development journey is to import the necessary libraries. These libraries provide essential tools and functions that simplify the process of building and training neural networks. Here's a breakdown of the libraries we're using. Import NumPy as NP, import Pandas as PD from Sklearn.datasets, import load iris from Sklearn.model-selection, import train test split from Sklearn.preprocessing, import one-hot encoder from TensorFlow.Keras.models, import sequential from TensorFlow.Keras.layers, import dense from TensorFlow.Keras.optimizers, import atom. NumPy and Pandas. NumPy, a fundamental package for scientific computing in Python. It provides support for arrays and matrices, along with a collection of mathematical functions to operate on these data structures. Pandas, a powerful data manipulation library that offers data structures like DataFrame, which makes it easy to handle and analyze data. sklearn, scikit-learn. Load iris, a function to load the iris dataset, which we'll use for training our model. It is included with sklearn. Train test split, a utility to split the dataset into training and testing sets. We could use Keras validation split, but as it's important to test on unseen data, this gives us explicitly visible separate datasets for educational purposes. One-hot encoder, a tool to convert categorical labels into a one-hot encoded format, which is essential for training neural networks. Keras has its own one-hot encoder as well, to categorical. TensorFlow.Keras, sequential, a type of model that allows you to build a neural network layer by layer in a sequential manner. Dense, a layer type in a neural network that is fully connected, meaning each neuron in the layer is connected to every neuron in the previous layer. Atom, an optimizer that adjusts the learning rate during training to improve the model's performance. By importing these libraries, we equip ourselves with the necessary tools to load data, pre-process it, build and train a neural network, and evaluate its performance. With this foundation in place, we're ready to move on to the next step. Step 2. Load the dataset. In this step, we will load the iris dataset, which is a well-known dataset in the machine learning community. The iris dataset contains measurements of different features of iris flowers from 3 different species. Our goal is to build a model that can classify the species of iris flowers based on these measurements. Here's the code to load the dataset. Load the data iris equals load iris, x equals iris.data, reshape for one hot encoding, y equals iris.target.reshape minus 1, 1. Let's break down what this code does. Loading the dataset. Iris equals load iris. This line uses the load iris function from sklearn.datasets to load the iris dataset. The dataset is returned as a dictionary-like object with several keys, including data and target. Separating features and labels. X equals iris.data. Here, we extract the features of the dataset, which are stored in iris.data. These features include measurements like sepal length, sepal width, petal length, and petal width for each flower. X is a 2D NumPy array. Picture a spreadsheet where each row represents a flower and each column represents a feature. Y equals iris.target.reshape minus 1, 1. The target labels, which indicate the species of each flower, are extracted from iris.target. The reshape minus 1, 1 part ensures that Y is reshaped into a 2D array with one column. This reshaping is necessary for the one-hot encoding step that we will perform next. By loading and preparing the dataset, we now have our features and labels ready for pre-processing. In the next step, we will one-hot encode the labels to make them suitable for training our neural network. Step 3. One-hot encode the labels. Neural networks require labels to be in a specific format, especially for classification tasks. Instead of having class labels as integers, e.g. 0, 1, 2, we use one-hot encoding to convert them into a binary matrix representation 0, 0, 1, 0. Each class label is represented as a vector where only the index corresponding to the class is 1, and all other indices are 0. This transformation is essential for training our model effectively. Here's the code to one-hot encode the labels. One-hot encode the labels. Encoder equals one-hot encoder sparse output equals false y equals encoder.fit transform y. Let's break down what this code does. Initializing the encoder. Encoder equals one-hot encoder sparse output equals false. We create an instance of one-hot encoder from sklearn.preprocessing. The sparse output equals false argument ensures that the output is a dense array rather than a sparse matrix, making it easier to work with. Fitting and transforming the labels. Y equals encoder.fit transform y. The fit transform method first fits the encoder to the data, y, and then transforms it into the one-hot encoded format. The resulting Y is now a 2D array where each row corresponds to a one-hot encoded label. For example, if our original labels were 0, 1, 2, after one-hot encoding, they would be transformed to 1, 0, 0, 0, 1, 0, 0, 0, 1. With the labels now one-hot encoded, we are ready to split our data into training and testing sets in the next step. Step 4. Split the data into training and test sets. To evaluate the performance of our model, we need to split the dataset into two parts: a training set and a test set. The training set is used to train the model, while the test set is used to evaluate how well the model generalizes to new unseen data. Here's the code to split the data. Split the data into training and test sets. Xtrain, Xtest, Ytrain, Ytest equals train test split X, Y test size equals 0.2, random state equals 42. Let's break down what this code does. Splitting the dataset. Xtrain, Xtest, Ytrain, Ytest equals train test split X, Y test size equals 0.2, random state equals 42. This function from sklearn.modelSelection splits the features X and labels Y into training and test sets. The test size equal 0.2 argument specifies that 20% of the data should be used for testing, while the remaining 80% will be used for training. The random state 42 argument ensures that the split is reproducible. Using the same random state will always result in the same split. Assigning the split data to variables. Xtrain, this variable holds the features of the training set. Xtest, this variable holds the features of the test set. Ytrain, this variable holds the labels of the training set. Ytest, this variable holds the labels of the test set. These variable conventions are pretty standard. X is your input data, Y is your output data. By splitting the data into training and test sets, we ensure that our model can be evaluated on a separate set of data that it has not seen during training. This helps us assess the model's ability to generalize to new data. Next, we'll build the neural network model. Step 5. Build the model. In this step, we will build a neural network model using the Keras sequential API. A sequential model is a linear stack of layers where each layer has exactly one input tensor and one output tensor. Most models are a sequential stack of layers. This API convention simplifies it. We'll add 3 layers to our model, 2 hidden layers and 1 output layer. Here's the code to build the model. Build the model. Model equals sequential. Dense 10, input shape equals 4, activation equals ReLU. This is the first hidden layer with 10 neurons, dense 10, activation equals ReLU. This is the second hidden layer, dense 3, activation equals softmax. This is the output layer with softmax activation for multi-class classification. Let's break down what this code does. Initializing the model. Model equals sequential. We create a sequential model by passing a list of layers. Adding layers, dense 10, input shape equals 4, activation equals ReLU. The first layer is a dense, fully connected layer with 10 neurons. The input shape equals 4, argument specifies that the input to this layer will be a vector of 4 elements, corresponding to the 4 features of the iris dataset. The activation equals ReLU argument specifies that the ReLU, rectified linear unit, activation function will be used for this layer. ReLU introduces nonlinearity to the model, helping it learn complex patterns. Dense 10, activation equals ReLU. The second layer is another dense layer with 10 neurons and ReLU activation. This layer further processes the data from the first layer. Dense 3, activation equals softmax. The output layer is a dense layer with 3 neurons, corresponding to the 3 classes in the iris dataset, and softmax activation. The softmax activation function converts the outputs into probabilities, with the sum of all probabilities equal to 1. This is useful for multi-class classification, as it allows us to interpret the output as the model's confidence in each class. By stacking these layers, we have created a simple feed-forward neural network. In the next step, we will compile the model, specifying the optimizer, loss function, and evaluation metric. Step 6. Compile the model. Compiling the model is an essential step that configures the learning process. In this step, we will specify the optimizer, the loss function, and the evaluation metric that the model will use during training and evaluation. Here's the code to compile the model. Model.compile optimizer equal atom learning rate 0.01, loss equals categorical cross entropy, metrics accuracy. Let's break down what this code does. Choosing the optimizer. Optimizer equals atom learning rate equals 0.01. The atom optimizer is used for training the model. ATOM, short for Adaptive Moment Estimation, is an advanced optimization algorithm that adjusts the learning rate during training to improve performance. The learning rate equals 0.01 argument specifies the initial learning rate. Specifying the loss function, loss equals categorical cross entropy, the loss function measures how well the model's predictions match the actual labels. For multi-class classification tasks, categorical cross entropy is commonly used. It calculates the cross-entropy loss between the true labels and the predicted probabilities, which helps the model learn to predict probabilities closer to the actual labels. Setting the evaluation metric. Metrics equals accuracy. Metrics are used to evaluate the performance of the model during training and testing. In this case, we use accuracy, which measures the percentage of correctly predicted labels out of the total predictions. By compiling the model, we configure it for training, specifying how it will learn from the data, measure its performance, and optimize its weights. In the next step, we will train the model using the training data. Step 7. Train the model. In this step, we will train the model using the training data. Training involves feeding the training data to the model, allowing it to adjust its weights to minimize the loss function. We will specify the number of epochs, which is the number of times the entire training dataset will pass through the model. Here's the code to train the model. Model.fit xtrain ytrain epochs equals 150, verbose equals 1. Let's break down what this code does. Training the model. Model.fit xtrain ytrain epochs equals 150, verbose equals 1. The fit method trains the model on the training data xtrain and ytrain. The epochs equals 150 argument specifies that the training process will run for 150 epochs. Each epoch involves one full pass through the entire training dataset. The verbose equals 1 argument ensures that the training progress is displayed, providing information about the loss and accuracy after each epoch. During training, the model adjusts its weights to minimize the loss function. This process involves multiple iterations, where the optimizer updates the weights based on the gradients computed from the loss function. As a result, the model learns to make better predictions over time. By the end of the training process, the model should have learned patterns in the training data that allow it to make accurate predictions. In the next step, we will evaluate the model's performance on the test data to see how well it generalizes to new, unseen data. Step 8. Evaluate the model. After training the model, it's essential to evaluate its performance on a separate test set. This step helps us understand how well the model generalizes to new, unseen data. We will use the test set to measure the model's accuracy and loss. Here's the code to evaluate the model. Header, evaluate on the test set. Loss and accuracy, model.evaluate, x-test, y-test, print test loss and test accuracy. Let's break down what this code does. Evaluating the model. Loss accuracy equals model.evaluate x-test, y-test. The evaluate method computes the loss and accuracy of the model on the test set, x-test and y-test. It returns the loss value and the accuracy metric specified during the model compilation step. Printing the results, print test loss, loss, test accuracy, accuracy. This line prints the loss and accuracy values. The test loss indicates how well the model's predictions match the actual labels in the test set. The test accuracy represents the proportion of correctly classified samples out of the total test samples. Evaluating the model on the test set gives us a clear picture of its performance in a real-world scenario. It helps identify whether the model has overfitted the training data, i.e., it performs well on the training set but poorly on the test set, or if it generalizes well to new data. In the next and final step, we will use the trained model to make predictions on the test data. Step 9. Make predictions. In the final step, we will use the trained model to make predictions on the test data. This step allows us to see the model's output and understand how it classifies new samples. Here's the code to make predictions. Make predictions. Predictions model.predict x-test. Print predictions. Print predictions. Let's break down what this code does. Making predictions. Predictions equals model.predict x-test. The predict method generates predictions for the test set, x-test. The output is a 2D array where each row corresponds to a sample in the test set, and each column represents the predicted probability for each class. The values in each row sum to 1, indicating the model's confidence in each class. Printing the predictions. Print predictions. This line prints a header indicating that the following output will be the model's predictions. Print predictions. This line prints the predictions array. Each row in the array shows the predicted probabilities for each class. For example, if the first sample in the test set is predicted to belong to the first class with high confidence, the corresponding row in the predictions array might look like 09, 0.05, 0.05, indicating a 90% probability for the first class and 5% for the other classes. By examining these predictions, you can see how confident the model is about each classification. This step completes our tutorial, demonstrating how to build, train, evaluate, and use a neural network for classification tasks using Keras. Congratulations on completing this tutorial. As you've seen, developing AI with modern libraries like Keras is not only accessible, but also straightforward. From importing the necessary libraries and loading a dataset to building, training, and evaluating a neural network, each step is manageable with just a few lines of code. This simple example with the Iris dataset demonstrates that you don't need to be an expert to start building powerful AI models. With these foundational skills, you're well on your way to exploring more advanced AI projects. Keep experimenting, stay curious, and remember that the journey of learning AI is a continuous and rewarding one. Embrace the simplicity and power of these tools, and you'll be amazed at what you can create.